SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of today's lecture is Online Predictive Task Offloading in Mobile Edge Computing. So, let us get started with understanding of predictive task offloading in mobile edge in MEC, that is mobile edge computing. So, as you know that edge computing, when applied to the mobile network, will bring into the benefits to the mobile users. So, how this predictive task offloading is happening in mobile edge computing, this is the title, this is the topic of this lecture. So, we have to see that online predictive task offloading, how it is going to be useful in mobile, bringing up the mobile edge computing. Online predictive offloading algorithm combines long short term memory LSTM and deep reinforcement learning, that is DRL, to predict the task dynamic information in real time. So, based on the observed edge network conditions and the server load. So, here when you say that based on the observed edge server condition and the server load, meaning to say that this will become the data for training up these models, and using this particular trained model, when a new information in the real time based on the observed edge network conditions and the server load is given, it will be able to predict the task offloading information dynamically, that is online. So, let us see about this algorithm. So, this algorithm makes offloading decisions by taking into account the task processing delays, task tolerance delays and the task computation energy consumption, and to avoid causing the network congestion and server overloading, thus minimizing the task drop rate and reduce the computational cost of the task. So, these are some of the important understanding or the requirements of the algorithm. Now, predicting the characteristics of a task, the edge server loads tasks are dynamically offloaded to the optimal edge server. Now, in this decision model, the prediction is combined with the task decision to dynamically allocate the resources for different tasks to further reduce the latency and improve the service quality. Meaning to say that this particular prediction model is further able to improve the latency, that is further reduce the latency. If it is not used, whatever latency was being minimized, it will add further minimization to the latency and also will improve the service quality. Therefore, the online predictive task offloading will make this particular algorithm or make this particular system mobile edge computing more functional, more affordable, or much better. So, let us see about the mobile edge computing system. So, here we have to now model the mobile edge computing system and a model. So, the model of a mobile edge computing, now we have to see that it comprises of multi-terminal, multi-edge, mobile edge, mobile network scenario, in which the set of terminal layer devices are denoted by M1, M2 and so on up to capital M and denoted by M. M means these are the terminal layer devices. Now, on each mobile device, that is MD, there exists a task queue and a computation queue. Here we can see that we are going to see the mobile device, let us say M, will with a computation with a task queue and a computation queue. where the task queue stores the task to be decided for offloading and the computation queue task to be decided for offloading, that is generated in a particular mobile device, let us say M. So, every mobile device will have this particular task queue. The task queue will contain the task to be decided for offloading, and then it will be having the computation queue which processes the task that are executed locally. So, locally executed tasks are kept in the queue that is called the computation queue of the mobile device. Now, additionally, the set of edge servers, that is the set of edge layer servers, are denoted by n. So, n are over here, that is 1, 2, 3, 4 and so on, they are the set of edge layer servers. So, multiple computation queues are included in each edge server for parallel computation of the transmission queues offloaded tasks. So, here you can see that this edge node n has multiple computation queue. So, multiple computation queue is used for parallel computation of the transmission queue offload tasks. So, transmission queue, that means those kind of jobs which are required to be offloaded, not to be computed in the computation queue, that is not for the local execution, they have to be put in the transmission queue, and this transmission queue will now communicate or connect to the computation queue of the edge nodes. So, for the mobile device, the tasks generated in different time slots are identified by t is equal to 1, 2 and so on up to t. So, for each arriving task, it is first stored in the corresponding mobile device task cache queue, and then the decision model gives this one here, and then decision model gives whether the task will be offloaded to be executed. So, once the task enters to be decided for the offloading, so it has to be decided whether it has to be locally executed or it has to be offloaded. So, if it is offloaded, then it will put in the transmission queue. Now, for a particular time slot, the new task generated by the terminal device M is denoted by lambda of M, that is what is shown over here. That is nothing but for a particular mobile device M at a particular time slot, this is the task which is being created. So, having understood this model of MEC, in MEC system model, when the terminal device M has the new task, that is lambda M of t in the time slot t, the decision model has to give the offloading scheme. So, the tasks considered in this model are atomic level tasks, that is the tasks are not subdividable, and each offloaded task can be executed in only one edge server, and the task offloaded to the edge server for the execution. So, I think let us see about the decision model. So, decision model is represented by the variable x m. So, x m will have two values, there is 0 and 1, that is a binary variable, denotes whether the task is to be processed locally or offloaded to an edge node. So, if x m of t is equal to 0, then it will be processed locally, and if let us say that x m t is equal to 1, then it has to be offloaded to the edge. So, this decision has to be made at this task q, that is lambda m of t. Now, the binary variable y m t is also 0 and 1, denotes whether the task is offloaded to the edge node n. So, here you can see that if y at a particular time t, y m t if it is equal to 1, then it is to be offloaded to the edge node n. If it is 0, then it is not offloaded to the edge node n. So, therefore, each task can be offloaded to one edge node only here in this particular model. So, let us see about the task prediction model. So, in the computation offloading system, a decision process is required after the task generation, and there will be a certain time delay from the task generation to give a decision. Although the task generation is dynamic and random process, considering the long term nature of the task, it will have a strong correlation with the time. Therefore, based on the history of the user devices, we can predict the task that will be generated in the next network time slot of the user device, and the load the service packages in advance before the real time tasks are coming. That is, allocate the best computation node in advance through the decision model, and this will make the prediction more effective in reducing further the latency and other cost. So, let us see the example that, for example, for any mobile device with a task data, let us say d1, d2 and so on up to dt, taking d1, d2 and dt as the input sequence into the trained LSTM model to predict the next time slot task data, that is dt. So, therefore, the optimization goal is to improve the accuracy of the task data feature prediction as much as possible. So, let me summarize here. So, summarization, we say that the mobile device with the task data, let us say dt is an element of d1, d2 and so on up to dt. So, now let us take this d1, d2 and so on up to dt minus 1 dt minus 1. So, this is for the t at time dt minus 1 as the input sequence, and this will be fed into an LSTM model, into a trained LSTM model predictions. So, if this is a trained LSTM model, when we enter it, it will make a prediction of the next data, that is dt at the next slot. So, therefore, this particular data is being predicted by LSTM beforehand, and thereby this optimization goal of the prediction model is to improve this accuracy of the task data feature prediction as much as possible. Now, let us see that if let us say that LSTM model based on that input sequence of the mobile user data, that is MD's task data, it can predict the next, what will be the next task will be predicted by LSTM model. Let us see how that particular model can be useful. So, as shown in the figure, in the real time we can predict the information of the future task by this prediction model and determine the decision and allocate the resources for the task. Now, when a real task arrives, if the error between the real task and the predicted task is within the allowed threshold, okay, so let us say that dt we have predicted, and here you have a real dt. So, if there is an error and if this error is allowed within a threshold, then the task is directly offloaded and computed according to the assigned decision information. Otherwise, the offloading decision is given using the decision model, and the information of the new task is added to the historical data as the training sample. So, by training the LSTM model, the weights and the biases of each gate in the network are updated to improve the accuracy of the prediction model. So, let us see through this particular flow diagram. Here we have to start with and train the LSTM predictive model and then predict the next task information, making the decisions, and if the error is within the threshold, then it will follow the decision to offload, and then it will add the task information to the training samples. Otherwise, if it is no, then it will put the new task information into the decision model to the making decisions, and so on. So, let us see about the load prediction model. So, the edge computing system offloading decisions may lead to the wrong offloading decision may lead to imbalance if the server load is not considered. So, the monitoring system on the edge server records system data and performance metrics such as CPU occupancy, network usage, and the current execution of the task. So, log data in the edge server can be used to predict the future edge server load, the number of idle queues or the edge nodes. So, for example, taking the edge server historical load sequence H1 to HT-1 as the input sequence to the trained LSTM load prediction model, the future load, that is ST, can be predicted using this. So, therefore, this is used as the predicted idle server, which can be preferred selected as the load computing node when training the deep reinforcement learning. So, load prediction model here in DRL training process, the actions are selected by the agent through a certain probability, that is the action with the largest Q value is selected with the probability epsilon, and the action is selected randomly with the probability 1 minus epsilon, and this is called epsilon greedy exploration in deep reinforcement learning. Now, this online prediction algorithm OPO uses the modified exploration and exploitation strategy, that is when the original agent selects a random action using epsilon greedy policy, the size comparison between the random variable rho and the probability epsilon is used to determine which action to take. This can be the random action for the random exploration or predicted or prediction action, that is the load prediction, that is the guided exploration, and that is what is shown over here. So, the actions for the load prediction guided exploration is obtained using LSTM. This type of guided exploration helps to avoid falling into the local optimum by giving the pre-selected action, that is the idle server in the actual scenario through the prediction action. It can reduce the number of explorations by the agent and improve the convergence speed of the algorithm. Let us see about the training process. So, the goal of deep reinforcement learning here, which is shown in this particular diagram, is to maximize the total reward by making the optimal actions in each decisions. Deep reinforcement learning often uses epsilon greedy for exploration and exploitation, which is the stochastic strategy which can fully explore the environment state, but it requires the long period of extensive exploration and a low data utilization. Now, in the online prediction algorithm training process, when the agent performs a stochastic exploration shown in the figure here, it uses LSTM to predict the load of the edge server to give an optimal action. So, here you can see that LSTM can predict the load of an edge server to give an optimal action. The optimal server at the next time slot is predicted by historical load situation, and offloading to the optimal server is done directly by this state to obtain a higher reward, also to effectively avoid the edge server load imbalance. Now, decision process. So, based on this historical records, the feature information of the next arriving task can be predicted by LSTM. Now, and the predicted information will be given to the reinforcement learning decision method over here. It can predict the task information, and this information will be given to reinforcement learning decision model, which is supposed to make the offloading decision for the predicted task. Now, when the real task arrives, if the error between the real task and the predicted task is within the allowed range, the offloading decision of the task is given directly, otherwise the decision is made according to the real task using the decision model. By predicting the information of the task, it can predict the target computation node of the task and effectively reduce the response time and the waiting delay in this particular system. Let us see about the MDP formulation of this entire problem. So, here in OPO algorithm, that is online prediction based algorithm. So, the states here, the state consists of the features of the task size, computation time, transmission time and historical load of the edge server. Here the state is shown, is expressed by the task size, then computation wait time, then transmission wait time, bandwidth, edge wait time and historical load. Now, the action consists of, the actions is the offloading decision to offload or not, whether to offload. It also includes the transmission power to be used to transmit the task to the edge server. So, here you can see that this particular action, whether to offload or not, and the transmission power is expressed over here. The action is 0 and 1, 0 means not to offload, 1 means to offload, and this action is given by xt, xm, ym and ptm. Ptm is the power, transmission power, where to offload, y, x means whether to offload or not. Objective function, that is called the cost. The weighted sum of the task execution delay and the energy consumption is the objective function, that is the cost. So, this metric what we want to minimize, that is the task execution delay and the energy consumption in case of the task offloading to MEC scenario is shown over here, that is the cost function. The cost function has following parameter, and this is the weighted, that is based on the time consumption at the mobile device, then time consumption at the edge nodes, and then energy consumption at the mobile device and energy consumption at the edge nodes are the important consideration here in the objective function, that is for the cost. Now, let us see about the reward function. So, reward is negative, the cost, that is the penalty term added here. The reinforcement learning maximizes the reward, introduces the negative sign, makes it equivalent cost minimization problem. Here you can see that the reward function RT will have the input of states at the action, will have this particular total time consumption, that is the T, which is expressed here in this particular equation, and the energy, that is E, and this is PT, that is the total energy consumption, and the task drop penalty. So, this becomes the reward function in the MDP formulation. Let us see the deep queue network with the target. So, deep queue network, that is DQN, there are two networks with the same structure, but with a different parameters in the DQN. One is called the target network, that is mentioned over here, and the main network, that is mentioned here, that is by Q. So, when iteratively updating the network, the algorithm first uses the target network to generate the target Q value as the function, as the label function ft, and uses the loss function to update the parameter of the main network. So, after the introduction of the target network, the target Q value generated by the target remains constant in time j, which can reduce the correlation between the current q value and the target q value and improve the stability of the algorithm. The target network will update the parameter theta and q network parameter theta in every step. So, that particular q value function, q value label, that is f t, is expressed here using r t and all that, and then it will be loss function will be calculated based on these particular parameters. Now, let us see about the double DQN. Double DQN is proposed to solve the overestimation problem. So, DQN takes maximum values with the maximum each time. The difference between this maximum value and the weighted average value introduces an error, which will lead to an overestimation after a long time accumulation. The double DQN is composed of two networks, QA and QB. It utilizes the two network to proceed the value state valuation and action output alternatively. That is, one network used to select the action and the other network is used to update the q value according to the selection action. So, double DQN make the learning process more stable and reliable by separating two steps of selecting the action corresponding to the q value and evaluating the q value corresponding to the action which eliminates the overestimation brought by the greedy algorithm and obtains an accurate q estimation. Instead of finding the label value of the parameter update directly from the target network, double DQN finds an action corresponding to the maximum q values in QA and then uses this selected action to compute the target value of the parameter update in QB. So, both of them network follows the Bellman equation, which is shown over here, that q values of A is updated and q values of B are updated using these equations, because they are different networks. So, both will be now being able to now eliminate the overestimation which was brought earlier by the greedy algorithms and obtains a more accurate q estimation. So, summary. So, what we have seen that double DQN is there to solve the overestimation problem. Of DQN, that is an epsilon greedy strategy. Now, this double DQN makes the learning process more stable and reliable. By separating these two steps of selecting the action corresponding to the q values and evaluating the q values corresponding to the action. Selecting the action corresponding to q value, and second one is to evaluating the q value corresponding to the action. So, this is one q network, this is another q network DQ1. Now, this particular q network will be used for selecting an action like here corresponding to to a particular q value, whereas the other one, that is the other network dqn, which will evaluate the q value corresponding to the action. Now, let us see about dueling DQN, that is the following figure show the architecture of a dueling DQN, where A and B layers, the network is decoupled into advantage layers and value layers. The advantage and value layers are computed separately and the q values are then derived from it. So, here you can see that this is an input layer and this is an LSTM layer, and here you can see that this is fully connected layer and this is what is called an advantage layer and the value layer. And the value layer. So, A means it is an advantage layer and B means it is a value layer. So, advantage and value are computed separately and the q values are then derived from it. So, you can see that the output q values are now derived based on this the action, the advantage layer, and all that things is being computed separately here in that end. So, this particular dual DQN can see that that LSTM layer will have these information as the input, that is the task, then training, computation and edge, and this is the historical edge load. All these things will be considered here in. So, let us see the results of an online predictive offloading. So, here you can see that the average task delay compared to the deep reinforcement learning and LSTM and DRL. So, average task delay, if you consider here in LSTM and DRL, if they are used both, it is quite less. So, here you can see that there is a difference. You can see that that particular task delay is reduced. So, here it comes out to be 6.5 and here it is 6. So, good amount of reduction is there if you compare the DRL with LSTM, using of LSTM, that is the online predictive algorithm. Similarly, in the other cost function, cost reduction, if you can see, then the cost also, as far as cost also is quite reduced here in terms of 10 raised power 3 into 0.5. So, you can see that cost also is reduced by applying the LSTM based prediction with the deep reinforcement learning. Now, number of drop tasks. So, here the number of drop tasks, if you consider with LSTM and DRL, so it is also significant in this way, but as the number of episodes are increasing, then it stabilizes. Now, here you can see that the average task delay, if you compare with that online algorithm, and if you compare by applying double DQN and dueling DQN. So, what you will find that here you can find out that that it is average task delay is quite improved in this particular case. In some of the episodes over here, you can see that dueling DQN is quite stable. compare to the DQN model. So, if you see this particular DQN model, it is quite stable. Similarly, the cost, if you compare here in terms of this DQN and the other models. So, this is the DQN. So, it is having higher cost compared to the online prediction algorithm. So, online prediction of offloading OPO, online prediction offloading algorithm, if you see the cost is quite less, that is quite optimal compared to the double DQN or dueling DQN application. Now, here you can see that the number of dropped tasks, if you compare, what you will find here is that the number of dropped tasks are quite less, and the number of dropped tasks are more in compared to the DQN is over here, and the number of drop task in OPO, online prediction offloading algorithm, is quite reasonable, good, and the performance. Further results, if you see that it is also able to reduce the network delay, and you can see that the network, as far as DQN is concerned, the network delay is of the order 5.6, whereas if you see the online algorithm for the same task, it is quite reduced here in this particular scenario, that is up to this point. And in between, that means it is much better than dueling DQN and dueling and double DQN. So, online prediction algorithm, you know that it is much better, even applying the other sophisticated DQN model, that is DQN and dual DQN. Further, if you see the cost comparison, and here the cost comparison cost is more in compared to the DQN, whereas optimal algorithm online prediction offloading is much better in terms of cost minimization. Task drop rate, if you considered here in all these algorithms, what you will find that this DQN is having drop rate more compared to the online prediction offloading algorithm. So, drop task rate is also much better compared to the other methods. Now, here the average task delays, if you see here in this case, it is also, you can find that your algorithms are giving the better results in these parameters. So, conclusion, in this lecture we covered the modeling the offloading decision making process using Markov decision process, and we have formulated the two optimization problems. One is minimizing the task execution delay, that is the optimization objective was solved using combination of LSTM based neural network and dueling deep Q networks. Then we have another objective we have found out is we have seen that jointly minimizing the task execution delay and energy consumption. So, the optimization objective is solved by combining the prediction model of LSTM and the decision model of DQN by combining the advantage of double DQN and dueling DQN. So, with this let us conclude this particular lecture. Thank you.